Hello everyone. Today, previously we had discussed on the Manish's algorithm, right? String processing algorithm. So today we'll be discussing on the suffix array construction along with the Kasai's algorithm for the LCP array, right? So again, what we'll be discussing today? Suffix array construction along with the Kasai's algorithm. So here, Kasai's algorithm for the this one LCP array. We know this, right? LCP array in the sense longest common prefix to find the longest common this one prefix, right? So let's see first what does suffix array indicates here, right? So let's get into the definition part here. A sorted array of all the suffixes of a string, right? A sorted array of all the suffixes of a string. Simple. This is the suffix array. A sorted array of all suffixes of a string. So it helps in efficient string pattern searching and solving many substring problems. This one suffix array. So let's get into the Kasai's algorithm here. This is basically an algorithm to construct the longest common prefix, right? This is the algorithm to construct the longest common prefix array from the suffix array in linear time. Fine, simple. Let's get into the explanation part here. So, a suffix of a string is just the starting from some index, is just the starting again, is just the string starting from some index till the end. We know this one, right? So, for banana, this one suffixes are banana itself, first thing. A, this one, this is also the suffix, and this one, after this one, we can just exclude A. Nana is also the this one, what do we call suffix ana followed by na and a. These are the suffixes. We know this one, right? Now let's get into the next point. The suffix array is simply the indices of suffixes, right? The suffix array is simply the indices of suffixes when arranged in lexicographical order. Lexicographical order in the sense dictionary order, right? So the order basically has to be in the lexicographical order. So if A and we have ACA, so lexicographical order of that one would be AAC, right? So if the this one, first of all, if there is ABC, this is in the sort, this is sorted, as well as, or BCA, it would be lexicographical order would be ABC, and if it is ABA, then the letter is repeated here, so the lexicographical order of it would be A and then B, right? So this is one simple example of the lexicographical order, right? So next let's move on with the next point here. The LCP array, or the longest common prefix array, stores the length of the longest common prefix between every pair of adjacent suffixes in the suffix array. This is fine. Now Kasai's algorithm, what it does here, Kasai's algorithm builds the LCP array efficiently in Pico using the suffix array and the rank array. So that's what it does, right? So these are some of the important points I wanted to discuss. So let's see the same thing in the action, right? So let's go with the algorithm or the example code, right? So now first let's go with the function to build the suffix array, right? So I'll just go with def here, build, this would be suffix and this would be array. Let me pass s here. This is fine. Now let me go with length of s. This is also fine. Now let's create an array of the suffixes along with their indices, right? I'll just go with the suffixes. This is fine. S. This is also fine. Now, comma I. So this one, yep, comma I. This is fine. Now let's do one thing. Let's go with the for loop here. For I and uh, range. Range we have to consider it up to n, right? So this is fine, man. So we are going with each element, that is nothing but suffix string as well as the index. We are considering this one in the form of each element, right, which consists of the suffix string along with its index. That's what we are going with. So now I hope this part is completely clear. Now let's do one thing. Let's sort the suffixes, this one lexicographically, as we had discussed the same thing within the, what do we call, explanation part, right? So now let's do one thing. Let's sort the suffixes lexicographically. I'll just go with suffixes dot sort here. This is fine. Then we have to extract and return only the indices, right? So as we are going through the build part, so I'll just go with suffixes here, or individual suffix we have to go with, right? So I'll just go with here. 1 second. Yep. Let me go with here suffix of this one would be 1 along with the 4. I'll just go with suffix in. Uh, Let me mention suffixes. Now this error should be gone. This is fine, man. Now this is fine. Let's move on with the second step. Nothing but the so um, we have went with the function to build the suffix array. Now, as per the explanation part, we have to go with a Kasai's algorithm to build the LCP array or the longest common prefix array. So let me go with simple function here. Kasai's this one LCP. This is fine. Let me pass the string along with SA. This is fine. Now let me assign this one to the length of equals length of s. This is also fine. Now what shall I do? Let me go with LCP equals 0 into n. Also let me go with this one is 0 into n. This is fine. This would be rank basically, right? Rank equals 0 into n again. This is also fine, man. Now let's do one thing. Let's build the rank array in the sense iterated value of the rank or rank of I will be or has to be equivalent to the position of the suffix starting at I in the suffix array. Meaning I can just write it in this way. For I n range this one n. So for I in range n, so let me go with the rank, man. Rank, so this one would be SA of I. So this is also fine. Let me assign this one to the I. So now this is fine. So let's initialize the k to 0, meaning so we have to go with the length of current LCP, right? So I'll just go with k equals 0. So let me go with for loop here for I in range n. So let me go with the if condition. If uh, we have to go with the rank this time, right? Iterated value of the rank. If the value is equivalent to the n minus 1, so we are going with the if condition here. So this is nothing but if condition is nothing but we are checking whether the last suffix in the suffix array has no next suffix, right? So that's what we are checking. So let me assign k equals 0 here and let me give continue. Nothing but we have to skip here. This is fine. Now let me go with j, man. J equals, so let's go with the next suffix in the suffix array, meaning j equals sa, sorry, in the sense j equals sa. Let me go with the rank here, rank of I. So this one has to be plus 1. This is fine. Now what we need to do, we have to compare the characters while they match. The sense I'll just go with while here I plus k less than n and j plus k less than n and s of I plus k is equivalent to s of j plus k. This is fine. Now within the while loop, k equals k plus 1. This is also fine, man. Now let's go with the LCP. We have to store the LCP length, right? So I can just write it on this way. LCP of rank. So what we need to pass here? Rank of I basically. Sorry. This one, let's assign this one to the k, right? So we are done this one. We are just storing the LCP length. After storing the LCP length, the last step is we have to reduce the length for the next iteration as well, right? So simple if condition. Let's write the simple if condition. If k is greater than 0, then k equals k minus 1, right? So this is fine. Now finally, let me return the LCP. So I'll just come here. So this one has to be return LCP. We have successfully written the algorithm. Now let's go with the test case or the example usage quickly. Right. So I'll just go with text. So let me give some this one. We have considered banana itself here, right? So let me copy the same thing here. Then the example. Let me pass same thing within the string. This is fine. Now let me consider here a equals. Uh, Let me go with the build suffix man. Build suffix array is the name that I have given. Right. So let me pass text here. Right. So we have to pass the text. Right. So LCP. Well, let's go with the Kasai's LCP. We have to pass text and SA, right? Text along with the build nothing but SA here. This is fine. Now let's print something for the interactive purpose. So I'll just go with print. So initially, let's just print text here. Meaning here we are just printing the banana, right? So this is fine. Now let's go with print. So I'll just go with suffix this one array. This is fine. Now let me pass SA, right? So this is also fine, man. Finally, what we will do, we will print LCP array. So this is also fine. Let me pass LCP. Yep, we are done with the algorithm part, right? So we are done with the algorithm part. So now, yep, we are done with the algorithm part, man. So before this one, checking the this one, I'll go with the whatever banana we have given, basically, right? Text. Let me explain you whatever we have written accordingly with the algorithm, right? So now, build suffix array. Let me come from. Let's start from the beginning here. This one, build suffix array. Basically, what we are doing here, we are generating all the suffixes that is paired with their starting indices. That's what we are doing, right? So now, next step is we are sorting them lexicographically. After that, we are returning only the starting indices, right? So this itself is the suffix array, line number 23. This itself would be the suffix array, main or suffix array. Now we are going with a, then we are going with a Kasai's LCP, right? So this one, Kasai's LCP. So what we are doing here, we are creating a rank array to quickly know where each suffix is in the suffix array. For that reason itself, so Kasai's algorithm is used for this one, longest, to find the longest common prefix, right? So here we are creating a rank array to quickly know where each suffix is in the suffix array, right? Then for each suffix we are comparing it with the next suffix in the suffix array to compute the LCP. That's what we are doing here, right? So this part, this is fine. Now finally we are making use of the trick of reusing the previous LCP length k for the efficiency. Previous this one, what do we call, we are making use of the trick of reusing the previous LCP of length k for the efficiency, right? So this is fine. Now we are done with the algo part, right? So we have considered the banana here, right? So we have considered, uh just give me a second here, we have considered text banana here, right? So now, what are the suffixes of banana basically? So here, this part, complete banana, then ANA, this one. Recall next, let me write here ANANA, and then followed by NANA, and then followed by ANA, then NA, then finally A. This is fine. Now this is the, these are the suffixes basically. Next, let's go with the sorted suffixes. When we sort this one, A comes first, right? So we are sorting this one lexicographically, basically, right? So this one will be the sorted suffixes. A, then comes A N A, right? So this is A N A, right? So then comes A N A N A, right? So this is the next one, right? So then comes banana, right? So when we sort this one lexicographical order, right? Banana. So this is fine. Then comes NA. Then comes the NA, right? So I had given the fantastic example, that's the small example that I said, right? So initially, this is the reason I said, right? For the this one, the example that I took for the this one lexicographical ordering, right? So if you didn't understand, just go back there and see, or you can just Google, you'll get it. It's not something that's very difficult. You'll get it. No worries. So now let's move on with the further things. Finally, we'll get NaNa. We'll get NaNa. This is sorted. This is in the sorted order basically. Right, sorted suffixes basically. Sorry. Now the suffix array would be 5, 3. This one is 5 basically. 5. So next comes, then comes 0, then comes 0, banana 0, right? So then comes this one, NF, nothing but 4. Uh, yeah, this one, NA 4. Then finally comes this one. What do we call? NaNa. So this one has to be 2. So this is fine. Now our suffix array is nothing but 531042, right? So this one suffix ending suffix, this one a, b-a-n-a-n-a, the last one, the index 5, a-n-a. So this one b-a-n-a. So this one b-a, this one a-n-a. So this one 3, right? 0, 1, 2, 3. A-N-A, right? B-A-N-A. This one A-N-A. 3. It ends at 3. So this one A-N-A, A-N-A, right? So this one quite obviously 1, right? So this is fine. Same goes with banana as well. This one N-A as well as N-A-N-A as well, right? So 0, 4, 2, right? So this is fine. Now the LCP array would be, or the longest common prefix would be this one, 1, 3, 0, 0, 2, 0, right? So the longest common prefix array has to be 1, 3, 0, 0, 2, 0, right? So this has to be the longest common prefix array, right? So this has to be the longest common prefix array. This is fine. Now we are done with the this one. What do we call? LCP array. We are done with the LCP array part. Now output that we need to get here is 531042 130020. This I have explained, man. Right. So now let's check the same. I'll just give here Python followed by file name here dot py. Uh, we have something here. Where is this? Line number 26, 26, 26, 26. So I have mentioned this one colon for no reason. This is fine. Now let me run this one again. Sorry, what happened to this one? Hey, yeah. Now text we are getting banana. We are just printing the text, right? So this one we are getting the desired output 531042 as we had discussed earlier, and the output that we need to get here is 130020, and output that we are getting LCP array, that also 130020, which is absolutely correct, right? So we are getting the desired output based on the algorithm, right? So again this one, so when I say this one again, I'll explain the output. If some people are like me, like maybe they don't get it at the first instance, this one at all, right? First time at all. Basically many times I don't get the things at the first time, I get the things at the second time mostly, right? So I'll just give here 531040 we got here. So how we got 531040 here? Sorry, 531042, right? Sorry. So this one is nothing but this is a, right? So this one suffix, the last one ending at the a, this one is A-N-A, right? So A-N-A 3, 0, 1, 2, 3. B-A-N-A, B-A-N-A, right? So the suffix A-N-A. So this this one, A-N-A, N-A. So this starts from this one. Uh, A, B, B after B, A-N-A, N-A, right? So this one is 1, right? So A-N-A, N-A. Then same goes with this one 0. We already have this one starting at 0. This one banana. So this is fine. Next, this one B-A-N-A. This one, right? One second. So NA basically starts, N starts from the fourth index, right? So this one is NA. So this one NA, this one starts from 2. Another one, right? NA we have to consider this time. So this one starts from BA, this one from 2, right? 0, 1, 2, this one NA. So this suffix, this one A starts at index 5. A this starts from this one index 3. BAN, this one A is the last three words, right? So this starts from the index 3. This is basically the starting index, man. In simple terms, if I would have said this one, I wouldn't have written this one actually this much big. This is fine. This is nothing but the starting index of the suffix. That's it, right? In simple terms, right? So basically now I'll also understand this one uh, clearly if I see this one after this thing. Uh, After some months, or yes, basically, right? So this is fine. Now we are done with this part, man. Basically I hope this part is completely clear. And what about 130020, whatever we have got? So this one we haven't discussed, right? So we know the starting index we discussed. So this one we got here, LCP array 130020. What is this basically then? So one is nothing but between A and ANA, right? So common prefix is A. Between A and ANA, what is the common prefix between A and ANA? A, right? So this one is A, BA, and the index is 1, right? So this is fine. Sorry, not the index, length. This time this is length. Sorry, I got confused here. This is nothing but the lengths. These are nothing but lengths basically, right? So this is fine. These are nothing but lengths basically, length. So this is fine. Now we have ANA and AN ANA, right? So the common prefix between ANA and ANANA is nothing but ANA, and the length is 3. This is fine. Now we have between ANANA and banana, no common prefix is found. So 0 here, right? 0. And between banana and NA, we don't have any common prefix. Again 0, right? So between NA and NANA, NA and Nana, NANA, so we have the prefix NA. So which is of the length 2 basically, right? So we'll be returning 2. Finally, last suffix has no suffix, no next suffix at all, right? So last suffix has no suffix at all for A. So this one will be 0 again. So this is how we got 130020, right? So this is how we got the LCP array, right? So I hope this part is completely clear, man. Is it understand, right? So now we are done with the suffix array construction and the Kasai's algorithm. So as we are done with the suffix array construction and the Kasai's algorithm, so we are good to write the code. Let's start. Sorry. We are good to discuss the summary part. Meaning, I'll just summarize whatever we have learned so far, and then we can finish it off, right? So now, just give me a second. 1 second. Did I forget anything? 1 second. Just give me a second here. This is fine, man. Yeah. Now, just keep these things in the mind. Some 2 to 3 important points I'll just discuss. Just keep these 3 things in the mind. Suffix array, what it does, it gives the sorted array of the suffixes using the starting index. So again, we know this one. I had stressed this one multiple times. What does the suffix array give? Basically, suffix array gives the sorted array of suffixes using the starting indices. So that's what we discussed, right? Sorting indices. This one, starting indices that I showed 540 something we got, right? So that is nothing but the suffix array that gives the sorted array of the suffixes using their starting indices, right? So this is fine. Now the next thing is Kasai's algorithm, right? Kasai's algorithm, what it does, it efficiently builds the LCP array in big of n, sorry. So that's what we got 10 something, right? So that is nothing but the Kasai's algorithm which efficiently builds the LCP array in big of n. Basically we make use of the this one Kasai's algorithm to build the longest common prefix in big O of n time, right? So big O of n time. So this is the algorithm which gives uh, basically this is the algorithm that is used to build the longest common prefix array in big O of n, right? So that is the reason we'll be making use of the Kasai's algorithm usually, right? Along with the suffix array construction. So build. whatever we had made use of, that is nothing but the suffix array, and the Kasai's algorithm basically efficiently builds the LCP array in big of n. So together, these two are very powerful, right, for solving substring problems like whether it may be pattern matching. Again, so we can just go with this for the pattern matching. If the problem, if any lead code problem or the CP problem which involves you to particularly solve with the they'll ask, sometimes they ask you to implement with this one particular algorithm itself. If you would have observed, many times they ask that problem can be optimized or that can be solved only with a particular algorithm, right? So in such cases, these kind of algorithms would be very handy, uh, right? So now again, Kasai's algorithm efficiently builds the LCPR and this one big often. Together, they are very powerful tools. We know this for solving the problems like pattern matching, repeated substrings, and mainly longest common substrings. Right. So mainly, Kasai's algorithm is used for the longest common substrings. Now, these three things you have to keep in mind. Now we know where to implement, how to implement, and what are the this one, what are its pros and cons, right? So let's finish it off for today, right? So this is it about the suffix array construction as well as the Kasai's algorithm. So tomorrow we'll be discussing on the suffix automation algorithm. For now, this is it. Thanks for watching, guys.